Hello, Accelerated Chemistry students. This is Ms. Krista Foley, and this is your Chapter 7, Section 3 notes all over bonding in metals. So, metallic bonds are based on the attraction of positive and negative charges between like metal atoms. So if we look at this picture, we have all silver atoms that are cations, and we have the electrons dispersed throughout. So the electrons are what we call in a C model. So within a metal lattice, metal atoms do not share electrons, and metal atoms do not donate electrons from one element to the next. The outermost energy levels of metal atoms overlap and form a C. Metal atoms donate their valence electrons to the surrounding C, and the electrons move freely within this C are called delocalized electrons. So here are two pictures of the electron C model. So these atoms, remember, are all positively charged because they're all metals. So they gave up their valence electrons, their outermost electrons, and now these electrons are being distributed throughout the cation lattice. So metallic bonds are formed from the attraction of the metal cations for the delocalized electrons. And remember, those delocalized electrons are the ones that are being moving through the entire lattice. So because of that, metals have different properties. So metallic compounds are, as we know, are good conductors of electric current, and this is because the electrons can flow freely in the metal. So as an electron enters one end of a bar of metal, an equal number of electrons leave the other end. So if we show the electrons flowing into the metal, we also have electrons flowing out of the metal, and that's how we can show that metals are good conductors and they will have electrical current, because remember, electrical current is from electrons. Metals are ductile, which means they can be drawn into wires, and they are also malleable, which means that they can be hammered or pressed into shapes. When a metal is subjected to pressure, the metal cations easily slide past one another. If an ionic crystal is struck with a hammer, the blow tends to push the positive ions close together, and the positive ions are going to repel one another and the crystal shatters. With the metal, it's very easy for them to do that because they have those electrons that are constantly moving throughout. And so it's not like that in an ionic crystal, as you can see in the second picture. So let's talk about melting points. We already know that mercury is already a liquid at standard temperature and pressure, and tungsten melts at 3,422 degrees Celsius. So they vary in general. They're moderately high though, which is due to the fact that they are in a very tight, crowded lattice structure. Boiling points are more extreme. Cations and electrons must be separated, which is going to require more heat. So if we look at the boiling points of metals, they will also range, but they're also higher temperatures than their melting points, which should make sense. Metals can also have thermal conductivity and electrical conductivity. Remember, the moving electrons move heat through a metal, making them good conductors. And the electric current is the flow of negative charge, and the moving electrons will carry a current through the metal. And let's finally talk about hardness and strength. So transition metals have moving electrons that consist of the two s orbitals and the d orbitals. So both the s and d orbitals are their valence electrons, and they will be donated to the c of mobile electrons. Because of this, they are going to be harder and stronger with the more mobile electrons a metal has. So now let's talk about the crystalline structure of metals. For spheres of identical size, such as a metal atom, several close packed arrangements are possible. So we're going to talk about common metallic structures right here, and there are three that I want you to be aware of. The first one is called a body-centered cubic structure. And so basically every atom has 8 neighbors around it. So if we were to look at this, we would see that that central atom has 8 atoms around it, 4 on the top and 4 on the bottom. So the metallic elements such as sodium, potassium, iron, chromium, tungsten crystallize in a body-centered cubic pattern. So it's a body-centered because you have the one atom in the middle, and then it's cubic because the other ones make a cube around that central atom. Another one is face-centered cubic. And so that is when every atom has 12 neighbors. So now think of a cube, and not only are you going to have an atom, excuse me, on every corner of the cube, now you're also going to have one on every face of the cube. So that means that every atom is going to have 12 neighbors. So this is consistent with things like copper, silver, gold, aluminum, and lead. And the last one is hexagonal closely packed arrangement, where every atom also has 12 neighbors. So this pattern is different from the face-centered cubic arrangement, and metals that have a hexagonal close packed crystal structure include magnesium, zinc, and calcium. So we've talked about metals. So now let's talk about what happens when metals combined. So now we have alloys. Alloys are mixtures of two or more elements, at least one of which is a metal. So an example of this is brass, and that is the combination of copper and zinc. Alloys are important because their properties are often superior to those of their component elements. So sterling silver is 92.5% silver and 7.5% copper. It is harder and more durable than pure silver, yet it is still soft enough to be made into jewelry and tableware. The most important alloys today are steels. The principal element in most steels, in addition to iron and carbon, are things like boron, chromium, manganese, molybdenum, nickel, tungsten, and vanadium. Steels have a wide range of uses and properties such as corrosion resistant, ductility, hardness, and toughness. And these are the ones that we will use most of the time in actual real world situations. Now, alloys can form from their component atoms in different ways. If the atom of the components in an alloy is about the same size, they will just replace each other in the crystal, and this is what we call a substitutional alloy. If we have elements where the sizes are different, then the smaller atoms can fit into the interstices or the spaces between the larger atoms, and we will call this an interstitial alloy. So if we were to compare these three, if we were looking at a pure metal on the left, notice that all of the molecules are the same in that picture. A substitutional alloy, so some of these blue spheres got switched in for some of the red spheres, and the interstitial alloys are for when you have elements that are smaller in size, and they will fit in the little spaces in between the metal atoms. And guess what? This concludes your Chapter 7, Lesson 3 video notes all over metal bonding. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbook, resources CD, and pearsonchem.com. Thank you so much and have a good night.